Okay, so where we left off, I was saying we will be using these three symbols for our subatomic particles when we get into balancing nuclear equations. Okay, so you will be seeing these a lot. Back then for a second to a word I said earlier that I assume you know, and that's the word isotope. The word isotope simply means atoms that have the same number of protons but different numbers of neutrons. Atoms with same Z but different A's. Okay? So if it like oxygen, or no, I used carbon 14 up there. The most common isotope of carbon is carbon 12. 6 protons, 6 neutrons. But there is a very famous isotope of carbon, carbon 14, which is radioactive, and we use it in what's called carbon dating. It's used to figure out how old things are when we find fossils. Carbon 14 is used in living organisms. So as long as we're alive, we have the same amount of carbon 14 in our body, us and a tree and anything else that's living. But as soon as the living organism dies, then the amount of carbon 14 begins to break down. And so when someone comes along and finds like a tree trunk from 1,000 years ago, they can take it, and by finding out the amount of carbon 14 in there, they can figure out how old it is, how long since it died. There's probably also a carbon 13 that's not nearly as famous, and I'm guessing there is. So these would all be carbons. They all have the same sets, but they all have a different amounts of neutrons, and so they're called isotopes of each other. Okay? Now, if you had something that was like 12.7, this is carbon and nitrogen here are not isotopes, right? Isotopes have to have the same number of protons, not the same number of neutrons. Every atom has more than one isotope, but every atom has one isotope that's the most common. And for carbon, it's carbon 12. Okay? And every atom has an isotope that's radioactive. Once you get to bismuth, set equal to 83, every isotope of every element above that is radioactive. But below 83, all of them have at least one that's radioactive. Isotopes hydrogen. So the most common hydrogen is 11H. But there's also a 21H and a 31H. This one is deuterium. Deuterium. E-R-I-U-M. And this one is tritium. And tritium is the radioactive one. These are often used in nuclear reactors, and we'll come back and talk about them as the unit goes on. Okay? So again, elements can have the same mass number, but not be isotopes. They need to have the same atomic number to be isotopes. All right, two other things in this intro. One is something that's called the atomic mass unit. Atomic mass unit. Usually in physics we use the unit kilogram for mass, but if we're talking about protons, neutrons, electrons, we're talking about 9 times 10 to the negative 27 times 10 to the negative 31. Kilogram is a huge unit to use. It's kind of like trying to measure the width of your hair in kilometers. It's not really very appropriate. So an atomic mass unit is a really tiny, 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 tiny unit of mass that we often use when we're talking about masses of atoms, molecules, and other subatomic components. Okay? We define an atomic mass unit to be 1/12 the mass of the nucleus of a carbon-12 atom. Okay? So we look at it then, like we know there's 12 nucleons in a carbon-12 atom, so 1/12 should then give us the mass of one nucleon. And so we define it. So 1U is equal to 1.66053886 times 10 to the negative 27 kilograms. Okay, so that's what an atomic mass unit is. It's really kind of then like the average of a neutron and a proton together. Or like weight, okay? So atomic mass unit. And so that will come up again as we go along. And then the one other thing for today, for the intro into nuclear, is the nuclear forces. So if the atom was the size of our classroom, then the nucleus would be the size of the tip of this pen. And therefore inside the tip of this pen would have to be all the protons and all the neutrons. Maybe not so bad when there's only 1 or 2, maybe even when there's only 12. But it shouldn't be too much of a stretch to realize that the more you pack into the tip of this pen, the more unstable it's going to be. And therefore there must be, oh, and by the way, at least half of what's in there, or close to half of what's in there, or some of what's in there don't like each other, right? There are protons in there, and protons being packed into something as tiny as the tip of this pen, there must be a really strong force in there holding them together, stronger than the electrostatic force of repulsion, because that would be pushing them apart. And before I go to talk about those forces, I guess I better clarify, for the record, the atom is not the size of our classroom. It's a fair bit tinier, which means the nucleus is not the size of the tip of this pen. It's a fair bit tinier. But still, all the protons and neutrons are packed inside. Like if you think of uranium, one of the most common isotopes of uranium is uranium-238. And uranium has 92 protons, and then the rest would be neutrons, all packed into something significantly tinier than the tip of this pen. You can see why uranium isn't stable. And you might have just noticed I called this uranium-238. We don't tend to say the lower one because we can all know what that is. We can look for it on the periodic table. But the 238 you wouldn't know unless I told you. All right, so nuclear forces. You're going to hear me say the words, just like I did in quantum, the words we believe here, because we don't know everything yet. So we believe there are 2 forces present inside the nucleus. They are brilliantly named the strong nuclear force and equally as brilliant, the weak nuclear force. We believe it's the strong nuclear force that holds the nucleus together. Okay? We know very little about the weak one, so everything that I'm going to say here will be about the strong one. We believe it's a very, very, very strong but short-ranged force. So if you think of the electrostatic force, it varies as 1 over r squared. We think the nuclear force, the strong nuclear force, varies as 1 over r to the 4th. So obviously if r is really, 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 really tiny, then this nuclear force is going to be huge. But as soon as r starts to get a little bit bigger, the strength of the nuclear force drops off. And that's why, so packed inside the nucleus, as long as the protons are really, really, really close together, then the force of attraction is going to be really strong. But when they start to separate a little, then it's the force of repulsion that will be stronger, and that's what makes the nucleus unstable. We believe these nuclear forces do exist between protons and protons, protons and neutrons, and neutrons and neutrons. We think that it's probably about 100 times stronger than the electrostatic force of repulsion. We think it's probably the strongest force known to exist. And it works really when the things are about 10 to the minus 15 meters apart, which is pretty darn tootin' close. All right, we'll come back tomorrow and talk about what happens when it's not strong enough to hold a nucleus together.